Recording in progress.
Okay, thanks, Dave. Okay, it's 9 o'clock. Let's go ahead and get started. So good morning, everyone in Vietnam, and good evening to everyone in the US. So let me go ahead and share my screen. Okay, you should be able to see my screen now, showing the Lecture 14 pre-assessment score. So in Lecture 14 pre-assessment, there are 16 questions, and out of 63 responses, the average score is 131, which is pretty good. It tells me that you guys watched the videos and read the lecture slide, so I'm pleased. Okay, so the score range from 50 to 160. So there's you guys got it all perfect, so that's great. Okay, so let's move on to the lesson. So last Monday or Tuesday, we discussed part 1, which is lecture 13. Today, lecture 14, part 2, and after today's lecture, which is going to be a shorter one, and then we'll have the last 7, which is cover CTS CTS 1, which is lecture 13, 14. Can you guys hear me well?
I can, yes.
Okay. Okay. Great. All right, so let's go to slide. Okay, regarding CTS topics, so last week we talked about the introduction objective inputs, the sanity checks, and also go over quite a few important terminologies in clock tree synthesis. So you know about skew, you know about insertion delays, and so on. So the first topic today is we're going to talk about CTS exceptions. Okay, so let's okay, so what exactly is CTS exceptions? So these are the endpoints in which CTS does not automatically recognize or consider as sync pins. So we'll go more detail what sync pins are and what endpoints are. So the reason they call exception because the user must instruct CTS tool how to handle them. So you have so these are exceptions that you have to tell CTS identify so that the tool know what to do with these endpoints. Okay, with these input. Yeah. So what is sync pin? So sync pin are clock pins of sequential cell or memories or macro with clock pins in which the CTS tool recognize automatically and use to balance clock delay and clock skew. Okay, so you know what clock delay, what clock skew are from last lesson. So sync pin is basically your clock endpoint, the clock pins of all the flip-flops in the design. So CTS will automatically recognize those as endpoint sync pins. Okay. So those considered as load for CTS, the sync point in pin. Okay, so that's what sync pin is. So okay. And so these are the 6 exceptions that we're going to discuss: stop pin, non-stop pin, exclude pin, floating pin, ignore pin, and through pins. Okay, so these are not recognized automatically by CTS. That's why they call exceptions. Okay, so sync pins or the clock pins of the flops of sequential cells. Those are sync pins and automatically recognized by synthesis tool. Okay, you'll hear this term a lot, sync pin, when you get to clock tree, sync pins or okay.
Bach, we have a question already.
Yeah,
Okay.
students asking, can you explain a little more about the automatically recognized by CTS tool in sync pins?
Yeah. So when you set up, when we get to when you do CTS, all the sync pins, which are the clock pins, let me see. Uh, let me go. Yeah. So let me go to the next slide and I come back to this. Okay. I'll come back so it'll make more sense. Let me go to the next slide. I'll come back. So stop pins. So let's talk about stop pins. Stop pins are endpoint of the clock tree that are used for delay balancing. There's two type of stop pin. One implicit stop pin, which is a sync pin basically. That's another name for sync pins or clock flops. So implicit mean automatic. That's something you imply something that means automatically recognized. So implicit stop pin meaning that the automatically recognized by CTS tool as a sync pin. So clock pin and flip-flops and macro pin are implicit stop pin. So these right here, so this is just a diagram of the clock tree simplistically. So these are automatically called sync pins or stop pin. So these automatically recognized by CTS tool as a loading of the clock pin. So that's the stop pin. So when you balance clock tree, you remember you started at a clock source and in at a clock pins of flip-flops. So the clock pin of flip-flops is considered as a sync pin or a stop pin, which is automatically recognized by the tool. You don't have to tell it anything. There are scenarios where you have to identify, you have to instruct CTS tool if they're not sync pins. For example, like you have a generator clock. Later on, we'll discuss that, but you have to tell them how to handle it. Okay, so here, this is called implicit stop pin or sync pin. The tool already recognized. You don't have to do anything in terms of tell the CTS tool recognize automatically and know what to do with them. Okay, so the other explicit stop pin is that user-defined stop pin. So there's a particular reason that you design, you want to tell the tool to stop here at specific point. You don't want a tool to traverse through this logic and balance through it. So you want to stop, then you tell the tool that you define this as stop pin, and the tool will stop there. It would not traverse to this uh, uh, to this logic. Okay, there'll be scenario like that when you need to do it. Um, okay, so let me go back to the questions. Can you some more about automatic recognized business tool sync pin? Okay, yeah. So this is a called sync pin. Sync pin basically are the clock pins of the flip flops. So when, like I said, when you start CTS tool, right, the CTS process, the tool has to know the starting point, which is clock source, the endpoint, which will be a sync pin, which is clock pins out flip flops. So when you define your SDC, which is constraint, you define your clock, and that clock the to read the clock in, it will know when it would traverse that clock. It will know what clock go where, right? Because based on the net list, it knows connectivity, and it know the clock go to this set of flops, and then maybe another clock will go to another set of flops. So these are sync pins of this particular clock source. So the tool will based on the connectivity to the clock source, the tool know which are the sync points or the stop pin for the particular flip flops.
I want to add, so the tool traverses the clocks, but it recognizes a sync pin by an attribute on the pin itself. So in this case, the flop has a clock. That pin clock, the tool will know by knowing there's an attribute. It say is clock or something like that. So the tool recognize those pins and automatically set them as sync pins, right? All the clock pins are set as sync pins. For example, if you have a custom cell and you define a pin and you want the clock to be to treat that as a sync pin, then you put that attribute in the .lib file. Say is clock pin or something of that nature.
Yeah. Thank you for that point. Yes, in your Liberty files, it knows. Yeah, the clock pin have a special attribute in them. That will say will identify as a clock pin. If it's not there, then you add the attribute to your to a particular pin that you want the tool to recognize as a clock. Okay, so there's another questions. Okay, thank you. Okay, so does that make sense? What is a sync pin in the design? So okay, so basically a sync pins all your clocks pins of sequential cells. So most all your flip-flops, your memories, and any other macros that has clocks. Okay, any more questions? Because the syncs are you need to understand these sync pins in order to do your CTS a debug, especially if you start having issue with one of the branches or something like that. You need to how to understand these and how to traverse the clock tree and figure out your issue. Okay, so the next one is called non-stop pins. Okay, so pin that are not trays, that are normal trays, are considered a stop pin. Okay, so pin that normally trace through as and normally considered non-stop pin. So by default, the tool recognize the following as a non-stop pin. So remember I talked about general clock tree here, show a general clock tree, the general clock circuit by 2, divided by 2. So normally, remember, for as a sync pin or stop pin, normally the tool will recognize a clock pin of the flip-flop as a sync pin, right? But in this case, this considered as a non-stop pin. The tool needs to trace right through this to go to this flop, right? So this is actually the sync point rather than this one because this is a generator clock, right? So in Innovus, it will recognize this is a generator clock structure and it will propagate right through here to this as a sync pin is rather than stopping here. Okay, so there's two scenarios. This is one that the tool will recognize as a non-stop pin automatically and traverse right through it. The other one is the ICG cell, which you should be familiar with ICG cell by now. So this is the clock coming in, right? So it knows that this is the ICG cell, there's attribute on it, and it traverse through here, and at the end, remember this drive the flip-flop, clock pin of flip-flop here. So these are the two non-stop pin that automatically recognized by the tool. So that if there are other scenario where you want the tool to stop a non-stop to trade through a certain logic, then you define that as non-stop pin. Then the tool will trade through. Otherwise, it will stop automatically. So there's a certain set of flip-flop or something like that you want the tool to trade through. Then you put a non-stop pin on that clock, and then it'll trade right through it. It'll become clearer later on in the labs that why you do this and so on. So once let me go through all the CTS exception, and maybe then you may understand the concept a little bit more. If not by then, just ask questions. Okay, and we'll try to answer as best we can. Okay, so again, these are the two types that the tool automatically recognize as non-stop pin that it will trace right through this. And this will be considered as a sync point of the clock tree rather than this flop. Okay, same thing with this latch. This ICG cell, it traces right through there, and whatever at the end of this signal, that clock pin will be a sync point. Otherwise, if you need know where you want to stop, you need non-stop trace through, you need to define it. Okay, explicitly define it.
And we've asked for clarification on the term trace through.
Trace through, that means it will go right through it. It will not stop here. So when the clock tree, when it starts tracing from the clock source, so CTS process, it will start tracing from clock source. I mean, it traverse the clock tree to every branches through to until it stops at the sync point. which is what a clock pin or flop or what you define. So trace through, I mean, it will not stop. It just following go, and then it'll stop whenever it recognize a stop pin or a sync pin, right? So that's what it's traced through. I mean, it just propagate is traverse through the clock tree.
And can you show me a page where you have a clock tree? I think we need to explain the tracing.
Let me go to the first page. Right. So
Yeah, go ahead.
no, go ahead. You go ahead.
I think we should have the clock definition and going through gating logic and all these flops and all generated clocks. I think we have to tell the students how the clock's nets are traced and where does it stop, right? Just a default first, and then they will know when we define something, because right now they don't know what tracing means.
Yeah, so tracing mean when the CTS process start, right? So remember, it starts from a clock source and in a clockwise, so it has to trace through. So here before anything happened, it'll trace through this clock source. Okay, here's one sync point. It'll stop here. So in between, okay, so they're all the clock trees, right? So it'll stop at a endpoint of flop, right? So in a case if there is the clock gating cells here or a divided clock structure, it will trace right through it. Okay, that's what I mean. Trace through. It will not stop there. It'll stop at a regular flops or a sync pin a stop pin that you define. Okay. So it figured out it has to know that so it can do clustering and balancing whenever it do CTS, right? So those are the otherwise it doesn't know how many loads, right? It has to figure out how many loads, how many endpoints, how many sync it has per clock trees, and the distance, where to sit at, the insertion delay, the current delay, and then it will try to balance by inserting buffers to balance all the different endpoints. So endpoints go sync pin, different endpoints here or sync pin, to balance the delay so that all the clocks will arrive at different flops across the chip at the same time or within that small clock skew window. Right? So before it has to traverse down and figure out all that before it actually does the insertion, the balance, and the delay. Until you have a better way explaining it.
I think I'm just go ahead and I'm going to look for a clock tree schematic. I'm going to try to explain the tracing later. Yes, go ahead.
Okay, we'll continue and I have different okay, so stop pin. Okay. So we talk about non-stop pin. I mean, it's trace right through it. Okay, so the next one is called excluded pin. So excluded pins mean that the pins that are excluded from clock tree skew, delay, or balancing. Okay, so for example, here, this is the clock source, and then it goes to two flops, and then this is the branded logic through here. So if you don't want the tool to consider this as part of when it building clock tree as an endpoint, you define a excluded pin here so that the tree will ignore this branch completely. It's only balance the insertion delay on these two nets. Okay, so exclude meaning not included in the clock tree, so it just ignores this completely. Okay, so it's only does these two in this particular example. So if you have the rest of the logic here, it will just do the rest of the tree here and ignore this branch. Okay, so that's exclude pin. Next one is called float pin or floating pin. So these are the clock pins that have a requirement for inserting delay and balancing, but they're usually to a macro or memory. So for example, here you have a memory here, okay. So in this memory, it has internal clock delay of 200 picosecond, right? And then your target here, your insertion delay to the flop here is 2 nanosecond, right? So you want to balance this branch to memory to be two nanosecond. So because the internal macro is already 200, right? So you want to match this up 2 nanoseconds. So you define this portion of the tree to be 1.8 here. Okay, so that's 2. So it matched the rest of the tree. So it's usually used for only memory or macro in terms because these are custom cells already, or the memory will be pre-built. It's already have a known, a fixed, known insertion delay. So you use it to tell it, okay, that brand needs to be 1.8. So the tool will put try to balance 1.8 here because it'll take up 200 picosecond here. So that's what float pin is. That makes sense? So yeah, so when you have memories in your design, you want to define float pins. Otherwise, if you don't define here, the tool put 200 picosecond here, 2 nanosecond here, and you add another 200, and then this thing becomes 2.2. So you have the skew, a huge clock skew because of this particular one. You misdefine a float pin on the memory, right? You don't define it here. The tool think, okay, oh, I'm going to balance everything to 2 nanosecond because that's a target insertion delay. It doesn't account for this. It doesn't know internally that it's all have 200 picosecond. So so you need to understand this, and then you define a 1.8. You account for that. So you define 1.8 for these branches. So the tool only put 1.8 versus 2. So that the whole tree will balance. Okay, so it's easy enough. Okay, any questions or comments about exclude pin or float pin? Okay, so Wei Yuan asks how can we measure memory internal delay? So the memory has already been built. It's already characterized. So when you get the memory, you will know those you will know the numbers. Those are part of the spec for the memory. So it comes with a spec sheet. It'll tell you the library models also. It'll tell you what the insertion delay from here to here is. So it's not something that you measure. It's already been characterized because this memory has already been laid out. So when they do that, they characterize those, this, and so it's part of the spec, part of the libraries. So you know those numbers. Okay. Okay. Any more questions before we go to the next page? Okay, so the last two type of pins here, exception pins are ignore pin. So ignore meaning ignore. Pin that are excluded from clock tree skew, delay, and balancing. By default, the tool recognize following pin as ignore pin, non-clock pins. So ignore pins, by default, the tool recognize as ignore pins. So non-clock pins of sequential cell output ports. So by default, those are ignored, so it doesn't look at it at all. It knows those are not sync pin. Okay, or source pin of a clock tree in a fan out of another clocks. So if it's down here stream, if it's a clock source of another fan out clock tree, it will ignore those. It knows as a source. This is very similar to exclude pin here. Ignore pin, but the ignore difference is that there are type of ignore pin that the tool does ignore automatically. So this is a little, yeah. Phil, do you just a side question, do you normally use ignore pin or exclude pin? There were
I seldom do these things, but occasionally we really don't define them until the logic guys tell us, right? So, and most of the time they are automatic. In some cases, yeah, you use ignore pin to do certain type of weird logic, but no.
yeah, so yeah, normally we don't know it up front at all because sometimes what happens is we go through a couple iteration of CTS run, and then some of the branches that happen to have bad skew and the results, and then we would debug it, and then a lot now some of the time because some of these branches here that not meant to be part of the clock tree, that the designer would know what the intention are. So they'll tell us, okay, you should exclude this from this particular one from this tree and so on. That's when we go in and we define them. But normally, yeah, you don't unless you know it up front. But normally we don't know. Okay. So through pins are trace through, right? So if you want a particular pin here, right? This is again just the example of the two flops. You want to trace through here, you just tell it trace right through it and go to this end. So a lot of time we normally don't do a lot of these unless design there's a lot of exceptions on the clock trees with a complex. So different kind of design will require different clock trees and different, I mean, for normally like a CPU, central processing unit, which I'm working on, normally we just have, one high clock speed. And other type designs used to work on telecom design, something like that. Some controllers, different type, will have more clock trees and they're a little more complex. Could have up to, 20, 30 different clocks. So those are more challenging in terms of defining on different clock tree and their interactions, and they may have a lot of these exceptions. Okay, so just understanding these terms, have it back in your mind. So whenever you actually work on a design in real life in your once you get a job, just keep this in mind. These are what they are. If you need them, you can always go back and reference and know how to look them up. You may not remember by then, but at least, hey, kind of ring your bell. Say, hey, ignore pin. We talk about through pin and nonstop pin. You can look it back up, and then you'll be able to understand them and then use it in your job. Okay, so we just finished all the
Yeah, so but can I send you a link? Can you bring up that link? I want to explain the tracing a little bit.
Okay, the VLSI tutorial DFT scan architecture.
Yeah. Just bring that up and zoom to the schematic.
This one?
Yeah. Can you make it bigger, full screen?
Absolutely.
So
Big enough? Or you want bigger?
yeah, bigger. Okay, so I just wanted to do a annotation. So I just want to show, sometimes instead of usually you have a clock definitions, right? And then you have flops, right? So flops, you have clock pins. Clock pins are really the stop. So if you have like one clock and there's nothing in between them, so the tool will have a net, right? Before the clock tree is built, there's a net. So the net is say, okay, this net is connected to this guy. This guy is connected to this guy. And it connect to, say, a NAND gate, right? By virtue, these are defined as clocks. Then the tool trace and say, this is a clock net. And this is a clock net, right? And since this is just not a clock pin, so over here is not a clock net, or I should say a clock pin right here. So anything between the clock definition point and the sync pins, you build clock trees, right? Automatically. So the buffers will be inserted. So these called tracing, but you have like a clock generation circuits that you have multiple definition. For example, over here, you have a clock defined at this point. And it goes to the divider, and it goes to a mux, and it goes to a bunch of flops. So tracing means that you define a clock here. The CTS tool will say, okay, I'm recognizing this is a clock net. It goes to divide by 2. I'm recognizing this is a clock net, part of this clock. So it's traced, and it goes through a mux, which is a combinational logic. So it will trace through it. So this one becomes a clock. So, and then it goes to here, and this combinational logic will have NAND gate, NOR gates, and at the end it has a clock pin, right? So that means tracing means go through here and we'll say, okay, this really is one clock trees. So when it builds, it will be insert buffers everywhere during that path. And it do all these calculation, and it has this one as one sync pin, right? And then all over here there are flops over here, right? That goes directly, from the clock pins. So we'll insert buffers, right? Because it's traced to the flop, so it's buffers here. So that's called tracing. So at the end, it looks at here and say, I have sync pins here, and I have sync pins here as part of one big clock tree. So it will try to skew balance between these two pins. That means that it will skew match, right? Between the flops here and the flop here. So the trees that goes through the clock dividers, that goes to the flops, will have to match the delays of all these buffers. So these buffers and the delay through here, they have to match. Unless you say this and this are two separate skew groups, then it won't try to balance between them. So tracing means that. So it goes here, you define a clock here, and it go through here, That means that now for this different clocks, it will trace and say, okay, I'm going to here, I'm going to here. So this is one of my section of the clocks. Now I go trace here and see a combinational logic is a mux. It will trace through it by default. Everything, so it trace here and it see all the flops here. So at the end, for this tree, it has two groups of flops, one over here and one over here, right? It trace through here and it trace through here through the combinational. So that's called tracing, right? So I hope that helps understand a little bit about how CTS works. It will have to trace first, and then and then you do exception. These are the default behavior, and then you do exception. Like I say, you can create different skew groups. So if there's no talking between these two, you don't want to match them, then you will say create skew group 1 here and skew group 2 here. That means if you don't do create skew group, then both of these will be matched. So this tree might be too long, right? Or in this top level, this tree might be too. This is only a few flops, and it goes through here through divider and to the mux and a whole bunch of flops. So if you don't need to, then you create two separate skew groups so that the tool won't put very long buffer chain here just to match the buffer delays here. So okay, that's all I wanted to explain.
Oh shoot. Okay, hold on one second. I was going to show you okay, so in this particular here, you have a division by 2, which so if it's simple with the 2 flops, back-to-back flops, then you would want to put a trace through pin on the second flop so that it can get to these mux. Okay, so otherwise the tool will stop right here. It would not go through this.
Or the more standard approach will create a generated clocks here. Right? So they need to know the create generated clock. They need to understand that concept, right? Yeah.
Yeah. Okay. Thank you, Phil. Okay, so hopefully after Phil explained, you guys know what tracing means. So before the CTS has to trace through different clock groups so that it knows how many sync pins are each of the groups, so it knows how to balance the different branches across the clock tree. Okay. Okay, so okay, so the next topic would be a CTS spec. So the spec is short for specification. So CTS spec mean basically your CTS targets. You specify what you need, what your target is, what you want out of CTS, what you want it to do. Okay, so it's short for specification. Okay, so what are all the things in the clock tree constraints or clock tree specs? Okay, so basically it's all the requirements for CTS, what you want CTS to do, what kind of target you want it to meet. Okay, so the first one, 2 things that are important are the clock skew, right? You need to find the clock skew. Remember what the clock skew is? It's basically the different arrival time at 2 flops or different flops in your skew group. So, okay, so that's the clock skew, and then clock insertion delay, which in turn is the used to balance the skew, right? So that's the clock delay to each of from the clock source to the sync pin of the clock pins. So that's 1, that's 2, and then your clock transition, right? How fast the clock transition from 0 to 1. And then you need to find the clock inverter or buffers that you're going to use. Okay. Yeah. Remember, you want to use the clock buffers. We in the last lecture, we talked about the difference between clock buffers and regular buffers. Why you want to use clock buffers versus the regular buffers, right? And then we need to define a clock skew group, right? By default, the tool will put everything in one clock skew group. And Phil talk a little bit about a clock skew group. I think we talked about last time also is you want to define all the synchronous clock that are related in one clock skew in one group. Okay, so you may have, depending on your clock structure, you may have multiple. Okay, and then of course the clock definitions. And then we you define the NDR rules, which is non-default rule. We discussed that in the last lecture. right? Like double width, uh, uh, double spacings, and perhaps shielding, right? And then you also need to define CTF exceptions, right? So we just discussed those. Also, usually I didn't mention here, but usually we set it's implicit. So when we define the routing rules, we tell it what metal layers to use in terms of the what layers to use for the prefer for the clock trees. Okay. And does anybody know? Let's stop here and ask questions. Does anybody know what we want to use? Prefer lower layers or upper layers for the clock trees, for routing the clock trees? You can type it in your chat and tell me why. If we want to use the lower, why? Want to use the higher layers, why? I think in the last lecture, I think, and Phil also discussed the reason also some of the reason. Anybody remember? Or just think about the lower layer versus upper layers. So usually the lower layers are much narrower, more resistant than upper layers in particular technology. So do you want to use narrow layers routes for the clock nets, or do you want to use a higher layer wider nets for the clock nets? Anybody want to take a guess? Okay. The thicker layers to prevent crosstalk. Okay. Yes, we want a thicker layers to prevent clock talks, to also prevent also to they have less resistance when IR drop. Yes. Wider for less resistant. Yes. Correct. Yep. Okay, what else? Okay, so what's the setback? If you use what is the negative or the disadvantage of using wider metal? Those are correct. What are the layer? What's the reason? What's the setback? What is the negative impact if we use wider routes for the clock nets? More area, it's take up more tracks. I think that I think you take more routing. That's take up more routing resource. That's true. More loading, exactly. So more loading, what does that mean? What does that translate in from the clock tree standpoint? What does that mean? It's more load, more capacitive load on the clock nets. That's correct. Yeah. Okay, keep thinking. So more load, more routing resource, but more loading on. So when Wu Tanan said consume more power, that is correct. Absolutely, that is the point to make. That's correct. So that is consume more power. Okay, good. Great.
So I want to address Ngô Thái how thicker to prevent crosstalk. Actually, thicker will make crosstalk worse because these clocks are aggressors, right? They're very strong. They switch up and down very strongly. So the thicker it is, the more coupling caps it is. It will not help with the crosstalk. It will make it worse. I just want to make sure you understand that it's not helping.
So the you see if you what happen is you have thicker wires, you're gonna and more loading, you're gonna need a bigger driver, right? To fix your DRV issue and things like that. I missed that. Yeah. So it's actually opposite. So that's why we need shielding. Usually shielding double spacing, double space and shielding prevent a crosstalk on the clock nets. Okay, thank you.
Yeah,
all.
so let's review why we want wider, right? But mention about EM, and we also mentioned about the need to really be sharp, right? So if you have a huge load and you have buffers, right, driving huge load, so if you have narrow wires, your rise and fall might be slow, right? Right, and rise and fall slow, rise and fall will affect. There's some short circuit current when you're very slow, so it will affect some of the short circuit. So you want it to be a little bit sharper, but not too sharp that will consume a lot of power and be the very aggressive signal integrity or crosstalk. But you don't want to be too slow, right? So is a trial and error, and by having also sharp edges, if you have slow rise and fall, then your skew might be worse. To help with the skew, then you want a little bit sharper rise and fall. So it's a complex trade-off that sometimes it's just understanding of what your circuitry is like. You can make the right choice in terms of the width and the spacing between the clock edges. So you hear about double width and double spacing. I wanna add more to that. So this is your clock signal. So if you do the normal spacing, then the coupling caps between these, you know, the double spacing is really to the signal. It's not between clocks. So this is, if this is a signal and this is a clock, and this is a clock. If you single spacing, then this cap is very large. So the aggressor of a clock tree going up and down strongly will couple into the signals and will make this signal be susceptible to noise, right, glitches. So by double spacing, where's the erase? Right. So double spacing will help you with
The coupling gap.
yeah. So this
Reduce coupling gap.
yeah. So reduces the coupling caps, right? So therefore reduce the glitch, the crosstalk effect, and a lot of times people prefer to do this than to do one of the options would be do shielding. So you put a ground or VDD here. This is ground or VDD, right? So if you do ground or VDD, then this is really a capacitor to ground. So there's no spacing if this is a signal. So you have a shielding between, between your clocks and your signal by having a ground in between here. But the problem with having a ground here, which is very solid, but it takes off a lot of resources for routing. So by just double spacing without the ground shielding, it just makes it, this is small enough that will do a job, right? So it relieves some of the areas for your routing, etc. Okay.
Yeah, so when you apply that NDR rules, so the router will obey those rules, because if it doesn't, when you check, it will report that there are violations there, so you know exactly. Unless it will obey when it has resources, meaning number of tracks, it will actually obey those rules. It'll keep that clear, that empty track for double spacing. Otherwise, they report in the report, and you know exactly if it's their violation or not. Okay, yeah, we talked about the crosstalk effect last time, right? On the clock nets. Okay, so let's see. I think. Okay, so where do we get the ST spec from? So in Innovus, the tool can generate the initial version for you, the baseline, what I call the baseline, or the initial version for you based on the SDC constraint and some of your setting that you actually set using Tickle. You see that in the lab. You set some of these Tickle command, set DB, and set your selection for your buffers and also the layer routings. So when you set that in a tool, and you tell the tool, go ahead and write out the spec file for me. So it will generate an initial version for you in Innovus. Okay, so in the lab, you'll see that happen. So it will contain all your clock source, which is including generated clocks. It's from the SDC constraint. Remember when we read in initially, we gave it the MMC file. It has the your constraint file, your scenarios, and your RC corners. You get it from the clock definition from there. Okay, you can all the DRV constraint on the clock nets. So those are max trend, max caps number, the same DRV that you learn on signal, but it's applied to clock net, and the values are different because the clock nets are very critical. So the DRV will be it's much tighter than the normal DRV on the signal nets. Okay. Ignore pins. So some of the ignore pins it knows automatically recognize it will in there. And also, okay, so when it spit it out, when it write it out, generate one, you can actually go in there and make changes, right? So it's creating a version for you, and based on your knowledge of design requirements from your designers, the RTL guide, the front end, they'll tell you what it need to be and so on, and you can make changes there, add additional SKU groups. Of course, if you have more than one SKU group that you need to do, you can add it, you can make changes there, right? Also, if the DRV is not tight enough, the designer want to make certain clocks transition much sharper, you need to tighten it up. Then you can also define some additional DRV constraints, and also you want to tie some insertion lane things that you can do it here. And then think in the lab, I have one example that you actually will do it. Okay. Also, you need to add additional, if there are additional exceptions, the exception, you can go in and define it here. Okay. So once you make changes to the spec that you're happy with, then that's where you can use that then start your CTS. So that's gonna be your constraint, your spec file, your constraint file for clock tree. That will drive the clock tree, what they need to do. Okay. Any inputs, any comments, or any questions? I think the next slide, believe I have example of a clock spec. So this is actually the clock spec for our lab for the design that we have. Okay, so the first section here, you can see these are ignore pins. Okay, so it define some M core pin, B pin ignore type, and then this other one here is ignore, say no clock trees, ignore. And in the follow pin, a clock source, so it knows set to be pin clock division, the Q pin is clock group true. So we have 1, 2, 3 clocks here, including scan clock, right? This is division clock, look like a generate clock, and this is the main clock, and this is the scan clock. Okay, and then it defines clock, and then it tells us, okay, create clock tree at name task. The source is clock scan. Okay, so we're telling it to create a clock, and then that's no SKU group. Okay, so if there's a SKU group, we'll name it here. And then set DB clock tree test clock CTS tree source max capacitance. So it's apply a DRV constraints, right? And then here it's just telling what the period is. So these are we get from RSDC constraint. So clock present and clock pin. So these are some comments that actually created by the tool. Okay, so my clock here, period timing function clock. So we create another clock tree here, and my clock. The source is the clock here, and it's default no SKU group. Okay, we have to go and define it by default. So same thing here, just repeating DRV here on the clock trees and also the period. And then it does the same thing again for the division clock. So it knows here it's a generator clock, right? And it does the same thing. It's a generate, and then for generated clock, it has to know the source and then the generated clock name. So it's repeated here, just the same thing for different clock trees. So those are the basic. I think this is the second page. Okay, so here it created initially no SKU group here, actually created a SKU group here. So command call create SKU group, that's name, and then you give us the source, okay, and then auto sync, meaning that okay, automatically figure out the sync point, okay, and then here you can see define the different targets here. So include sort latency, constraint none, create clock. So all this different type of SKU group, 1, 2, and different constraints. Okay, it got chopped up here, but so it define different one through here 1, 2, 3. Okay, there's so 3 different clocks, 3 different SKU group 1, 2, 3 for the particular design that we have. Okay, so these are the default one. Okay, so that's the I think in the lab I had you guys doing additional constraints on this. There's no do you notice? So what's missing in here? Anybody? Can anybody tell me what's missing in this clock tree spec? So here define a clock, right? And here you got SKU group. What's missing? There's quite a few things missing in the clock tree spec, the default one. Two most important thing I'm missing in the clock tree spec. What is the high priority? Remember one of the slide in the last lecture? The highest priority for CTS, what are they?
I mean target SKU.
That's right. The clock SKU is missing from here. The target clock SKU. And then one more. You can type it in if you don't want to speak. Type it in there. There's one more. So clock SKU is one of them. What's the other one? Okay, we have NDR. That's also true. Yes, but that's true. The NDR is also missing from here. But the other one, along with clock SKU, I'm thinking is latency delay. That's correct. Is the insertion delay, right? So we have to define insertion delay for as a target. So it's missing from these, right? So in the lab, we do it in addition to this. Okay, so this is the basic that the tool generated for us. Okay, good. Yeah, the NEO is not here, correct? And the layers, the number of layers, what layers we want to use. So a design has 9 layers. Do we want to use on number like 1, 2, 3, 4? So that's also missing from here.
So I wanna add something about the methodology. We speak about target insertion delays, right? So one thing is the relationship between the target SKUs. So if you want small SKUs, generally you have longer latency, right? The insertion delays. So in practice, a lot of times we don't have target insertion delays, but we have target maximum SKUs. And sometimes the default will be just 0, I think, if you don't specify any target SKUs. Maybe depends on the tool, but but you can set target skew at 0, so the tool will work as hard as it can. And at the end, you see what the resulting skews are when it tries its best. And then you can see what the resulting latencies are, the clock insertion delays are. If they're not excessive, then you just go with that. The problem with defining the target latency is that you don't know what will be optimum. And so it's just something you need to understand the relationships and also the impact of different constraints here, so that you can make the right decision in constraining the clock trees. So clock tree synthesis is one of the most, if not the most important flow part of the flow in terms of time enclosure. You don't do a good job here, you will have harder time closing timing, or if you close timing, your design is not as optimum as if you do the better clock tree. So
Yeah. So what if you said most optimally it run as fast as it should? Yeah, that's what I mean by optimum. So yeah, so in and he's right. So sometimes you because most of the time we have target on a type of design, we know exactly what we need, but in case in the event that you have no idea, brand new design, you have no clue on what it can do, you can let the tool don't define, actually you don't define any target, the tool automatically will figure it out, and it'll give you, and or you can define as at 0, then it'll do the best it can, of course, that at expense of other things, right? Nothing's for free. So you have to make a trade-off. So if you know it, then we'll add it in here. Okay, if you don't put it 0 or you don't put it all, and then the tool will automatically figure it out.
yeah, and one additional thing to note is this: the CTS spec is not needed in very simple design where you have complete SDC. The tool will read SDC in and will generate the CTS spec on the fly and use a CTS spec. So in simple design, you don't really need to define anything additionally. You can even define all those different constraints using TICO files outside of the SDC. So in a lot of cases, you don't really need to mess with this at all. But these things create skew groups additionally are really design dependent, right? And these are really complicated to use because clocks CTS spec is really not a straightforward format. So it's a personal preference, but a lot of times I use the TICO files, the TICO command to do what I want instead of my, going with the complex modification or additional lines in CTS specs, because CTS spec is really clunky in terms of format. So you'll play with it, and you will man page of the different TICO command that allows you to do CTS spec, but in like executable TICO command versus going here and do individual commands like this. But it is something with experience, you have your own methodology and flow. Yeah.
Yeah. So for similar designs, it's straightforward. And he'll say, for our lab, which is simple design, you can go with the default one and let figure out. But I'll have you guys do additional one. Okay. In the next one, we'll talk about different type of clock trees and when to use it. So you different scenario. Okay. So that will also give you a picture of the complexity of the clock trees and how important it is for you to build the right clock trees and to meet your target and the impact. Dave, I think it's time for a break, right? Let's take a 6-minute break. Come back.
Yeah. Did we say happy birthday to you, but
No.
okay, students, today is But's birthday, so
I turned 21.
Only one in hacks, right?
21 in X, thanks. Yeah.
All right.
All right, let's take take a 6 minutes break. Let's come back at 10:10 because we have a few more slides to cover and then go over the labs.
All right, I've got a clock started. I'll start sharing it to the screen.
Okay, so okay, it's 10:10. Let's go ahead and get going again. Okay, so the next topic is type of clock trees. Okay, there's basically different type of clock trees you can build. So I want to introduce you to 5 different one. Okay, and talk about their pro and cons or advantage and disadvantage when to build them. Okay, so there are 5. The first one is called conventional single source, and then we'll discuss about a clock mesh, and then another type called what's called H tree, and then the fishbone. The reason it's called fishbone because it looked like a fishbone structure. Okay, and then a multi-source. So this is 5 different one. Okay. So there may be other types, and they call a variation of it, but these are the 5 main one. So what is conventional clock tree or single source? The single source meaning it's a single clock source. So it's also sometimes they call it a conventional CTS because by default, most CTS tool will build this structure. Okay, what's called a single source or conventional clock tree. So it consists of you can see clock source and then the clock tree cells and then the clock creating buffers and then your loads. Your loads which are your sync point, right? This is a different flip-flops on this different branches here. So this single source pretty much is suitable only for low frequency design, simple design that has low sync count. Low sync count is meaning less, low number of flip-flops. So it's suitable for that. It's not suitable for high frequency or design with large number of flip-flops. Okay. It's low power consumption because there's only a few branches, and a few level of buffers. It's low power. That's the reason it's low power consumption. It also is easy to do clock gating because if you need to shut off these branches, you just move the clock gating structure up to here and then shut up entire branches here, right? That's the reason it's easy to clock gating. The disadvantage, those are the advantages, right? The disadvantage is sensitive to chip variation, which is OCV on chip variation, which we discussed, right? It's sensitive to that because it has multiple paths. It has less common path from clock source to sync, right? There's multiple different paths. So when you have multiple different paths, there's many elements in between. So it's prone to more to OCV or variation in the path, right? So it's more variation that mean the clock skew. Okay, the clock skew is going to get various also. Also because of different branches, tend to have high insertion delay. Okay, so and it's difficult to achieve lower skew. So these are the disadvantages. So most simple design, straightforward. You do straightforward CTS where you don't have to do any manual. This is automatic. Okay. So for most small block chip, low frequency, this is the easiest way to implement the clock tree. So in the lab, this is what you're going to be building. It's just conventional single source clock tree. Okay. Any questions or comments? Okay, we'll go to the next one. So the next one is clock mesh. The reason it called clock mesh is because after the it has a mesh in between here. So you have in this structures, you have a clock source. You have what's called pre-mesh driver, and then you have mesh driver, and then you have your mesh, which consists of these Y wires, and then you have your clock gain receiver, and then you have your load. Okay. So what's the advantage of building a clock mesh? You can achieve lower clock skew. Okay, it has high tolerance for OCV because it has more common path from the clock route to sync, right? So you can see different path to the mesh area share. So if there's more common path, that means there's less chance of having variations on them. You have more path, like the single source, you have higher chance of OCV. Okay. So you can see there's just a fixed number level of buffers, so you tend to have low insertion delay on this type. Okay. The setback or the cons is that I tend to have higher dynamic power consumption because you have a lot of these parallel drivers here, right? So these are bigger driver, and you have higher capacitive load because of this mesh. Remember, high capacitive load is going to cost more dynamic powers, right? It's also take up more routing resource to create this mesh. Okay. And it's also because there's so much because of this mesh, you can't really move. It's difficult to do clock gating. You can't really move it up here to do clock gating, right? Because there's no way path to go through. So you can only do it at the low level here. Okay. And the other thing is the tech time compared to the single source. It takes more time to implement. So you will have to build this mesh and everything. Okay. You have to do all this, so it take more time. But the advantage is you have low clock skew. Okay. So on a more bigger design and more complex where you need lower skew, and if you do if you happen to do a design in a lower geometry node, you would want to build this kind of mesh because it's a low geometry node tend to have the OCV are much higher. So you want to build this kind of structure where it's less prone to OCV. Okay, question, inputs, or comments from other instructor? Oh. Okay, so let's go move on to the next one. Perhaps we'll go through all 5 of them, and then you can gather your thoughts, and then perhaps have questions then. Right, the next one refer to is what's called H tree, because the way that we build the driver here, you can see it's kind of a big H, like a big H here. The way the driver is, or the driver is placed. So it is possible to achieve low skew. It also good tolerance for OCV because it has a lot of common path. Okay. From source to load or endpoints. It has lower power dissipation compared to clock mesh, the previous one. Okay, and also less routing resource compared to mesh because you use the clock tree, the H format instead of whole mesh. However, it has more level of drivers, so there's going to be higher insertion delay. It also difficult to require manual to avoid macro connection because if you have a macro block in between and you need to do a clock mesh or an H tree is kind of difficult. So you have to plan up front. And you also need the super driver to drive this mesh, right? This is a super driver buffer. What I mean by super driver is the large clock buffers. We refer to as super buffers. And different technology have different super buffers or the high drive. Okay. So we'll need that to drive because you have to drive this in a whole H tree. Okay. So it's recommended you always, if you use H tree, always want to UNER rules to avoid SI or EM. Okay. So these are my experience I share. Until or any other instructors go. Okay. If you guys have additional thoughts you want to share, go ahead.
Did you finish all 5?
No, I still have
I'll
2
make
more.
some comments. Right. Yeah, go ahead and finish all 5.
Okay. Students, you have any questions? We still have the fishbone structures and the multi-source. Okay, so next one is called fishbone. The structure on the bottom before the drivers, it looks like a fishbone structure. So you put a super buffer here also, and you have this fishbone structure that will fan out to these loads here. Okay, that's the reason it's called look like a fishbone. So they call it fishbone structure. So the advantage of this is less wiring than the H3, small sensor delay, consume less power, but it tend to have a larger clock skew than the H3. Okay, because there a lot of quite a few on the fishbone. There are a lot of endpoints on per H3. Okay, and the last structures was called a multi-source clock tree. Okay, so it basically is a combination of the conventional clock tree and a clock mesh. So this is conventional, and you see a clock mesh being built down here. So that's what I refer to as a multi-clock, multi-source clock tree. So it has a higher number of common paths than conventional clock tree, which make it more OCV more OCV, immune to more OCV, so it tolerate OCV better than the conventional clock tree because of more common path down here. It consumes less power than the clock mesh. Okay. Okay, due to the fabric, due to the coarse mesh here. Okay, so require less routing compared to clock mesh. It has higher flexibility for implementation for macro dominant design in comparison to clock mesh. Let's see, I put that here. High flexibility implementation for macro dominant design. Okay, I see. So the reason I put it there because if you have a macro dominant design, meaning you have a lot of memories design, then because the combination clock mesh and single is more flexible to implement versus just a clock mesh straight up because you have actually additional buffer layers to deal with, so it's easier. Okay, less skew comparison than conventional clock tree again because of the mesh. Less insulated, ease of power gating. Okay, it's ease of power gating because of the similar to the conventional clock tree, right? You can come up here and you can shut down a particular area. So yeah, I don't normally deal with too much of this particular clock source, this multi-clock tree.
What did you choose for the last 3nm design that you taped out recently, and why?
We built it's a combination of mesh and H3. We have these big spine and we put some buffer in between. It's not quite H3, it's a combination of the two. We had a mesh that distributed the clock throughout, and then we had this super spine clock tree on the top layer metals, Y1 and super buffer space them evenly to balance out. So we did a combination of the two.
So you have a mesh for every clocks, or you have only one single clock?
We have a mesh for every branch of the clock because we really have only one main clock in the CPU design.
So you have separate meshes.
We have separate mesh for different sub block. That's correct. So we at the top level we have a big spine that divide up to different blocks below blocks, and then we have different mesh, and then we have
So you have H3 and mesh. So
yeah, it's a combination.
Isn't that the last one that you mentioned? You say you don't do the last one, but what you describe is just like the last one.
Not yeah, we don't do this. I'm sorry.
That thing, right?
This one we have a mesh, but we don't do exactly. We have up here we have a spine that actually
Yeah, the spine,
Yeah.
the H3, right?
Yeah.
So you
So
if you're doing multi,
yeah, it's not exactly like this one.
yeah.
Yeah. Yeah. Okay, so to summarize, so we have 5 different one here. Okay, so this is pretty much the end of today's lessons. So until you have additional inputs or the student you have comments or questions, go ahead.
Yeah, can you give them a guidance if it is not a microprocessor, right? It's just a mixed signal, say a RISC-V base or an ARM based IoT chip. Which of these five would you recommend?
When I did the those small chips, the little ones that not high speed, this is what I go with first. I just let the tool does it. If it meet my spec, I'm go with it. Like you said, right? Unless somebody tell
Right.
you.
So wouldn't you recommend even the H3?
Yeah, I mean, if you got time to do it, the H3 you can do it. I mean, as long as you meet your target, right? And your speed. So it's really dependent on the speed of the design. Most of the time when I did the mixed signal design, it tend to be a small digital.
Right.
They're not very high speed. They're not very, timing is not that critical. Okay. If you meet your power spec on this guy, because it's automatic. Okay.
Right.
But, if it does not, where you have to go and handcraft, then normally we just go to the either X3 or the fishbone.
Right. So when you do, yeah, I think it's important for the student to know what we mean by H3, right? Can you describe the process of building the physical and where you put all these buffers and how do you use CTS, right? Or are we gonna have that in the lab for H3?
No. This is, I think it's more on a not the basic part of CTS, the class. That's gonna be require more details, right?
Right. So
So
yeah, so students, you're gonna learn just the left one, right? Conventional single source.
yeah, so
For the
this is
fundamental class. But yeah.
yeah, I didn't think we have time to go in that detail because for just the basic class, I wanted to introduce the student to the, what is CTS, what are the different one. But we just build the we only have time to build because the lab that we have, we only be able to build the one on the left, the conventional clock tree single source.
Right.
Yeah.
Okay. Thanks.
Okay, students, you have any questions before we do the labs? We go over the labs. Okay, so I assume that you don't have any question, mean you understood everything we talked about today, right? If you don't understand something, go ahead and ask. We will try our best to answer your questions. No question is dumb questions or whatever. Okay, you don't know, just ask. That's how it is at work. If you don't know, go ask somebody who knows. Then you'll know because that's that you get the job done in the real world. If you don't know, go ask somebody who knows to guide you, and then you get the job done versus just sit there for days and not asking, and then you be late. You be late because they rather you raise your hand, you don't know, then you get it done and you know next time versus not knowing.
Yeah, so CTS is very complicated. Yeah, if you don't understand deeply enough, then please let the teachers know so we can do certain additional explanation. Otherwise, it will be assumed that you understand it.
Okay.
Well, there's a question right there.
So Wing Lemon asking, can you explain the next to last question in pre-assignment? Okay, I don't know what that is. I did that a while back. So let me switch gear and go pull that question up. Um, Okay, let me go here and let me find out what the question is. Okay, bear with me here. This thing's huge.
He mentioned the question, what impact, if any, on the design if not all setup timing violations are fixed?
Oh, okay. So what impact if at all design if not all set time is fixed? So I kind of alluded to this earlier. Let me just bring the questions up. I have it. I have it here. So the student can see. Everyone can see the. Okay, what impact if any design is is fixed? No impact of design. Design will not function as expected. Design runs slower. The real time faster. The correct answer would be design runs slower. This is setup time, right? So if your design is, let's say you target to run at 100 megahertz, right? And and if you design you run at not you violate by 100 picosecond. Let's say you run at 99, so your design just runs slower. It doesn't the functionality still should work. It just runs slower versus hole, right? If you don't fix all the hole, you're gonna have a problem. The design will not function as expected, right? So this just runs slower. So for example, a lot of time we add extra margin. Let's say we're trying to design a CPU run at 2 gigahertz, right? So we say, okay, let's pad it. We're trying to target at 2.1 gigahertz. So if we don't fix all of them on the last 10, 20 picosecond of the design, so what happens? Your design is just going to run at 2 gigahertz versus 2.1. So that's all it does is it just runs slower because now that's all it does. It doesn't impact the functionality. But opposite, your whole time you don't fix it, you're gonna have issue. So you have to fix all the whole time. Remember when I talk about the whole time, you have to fix all violations in the whole time. Okay, otherwise design will not function.
So I want to add to that two things. One is that slower, meaning that you have the chip back in the lab and you have an evaluation board, you have a chip in, and you run at the speed and it doesn't run, then you can lower the frequency of the input clocks and it will run. But if you have whole time problems and no matter what you do with the frequency, it won't run accurately functionally because it has problems functionally and it's not speed dependent. But the second part that I want to add for the setup is that a lot of times, people, including myself, we sign off with negative slacks and with the understanding that everything is simulated, right? Everything is modeled and simulated. So when you have 3 sigma, when you're simulating the worst case, assuming certain kind of distribution of your parameters, and when all the parameters are really worst cases, and you have from 3 sigma and you have 3 parameters. If you use 3 sigma on each, you're simulating at 9 sigmas, right? So in a lot of cases, just a numerical number that a lot of times you say, okay, because of this and that, we're okay with having negative slack on the setup. And when you get back in the labs, chances are you're gonna just have the fast enough silicon. So it's not like a black and white thing that you cannot sign off with negative slacks. And in the past, when I was designing, coming from designing with a Motorola process, and I came to Intel, and I designed a DSP chip, and my chip became the fastest DSP in the world because I was designing with the expectation of a Motorola process. but Intel process was far superior, and the Gaussian distribution was a lot tighter. So when we sign off with some negative slacks, in reality the silicon is super fast, right? So just something that you need to be aware of, because not everything is math. A lot of these things are statistical, and all the parameters are modeled.
Yeah, so yeah, thank you, Phil. Yeah, so I mean, we hadn't talked about the silicon. There's a bell curve on size. Some silicon will be much faster than others, right? So most of the time, what happened in the this is just in like Apple, right, or any Samsung or us, we design CPU to target at let's say 2 GHz, right? But then the silicon come back on a good lot, it can run at 2.4. So we take that and say we run at 2.4. So we're always going to market the fastest one, right? But so some of the CPU may on your phone may run at 2.2 or something like that, right? It depends. So yeah, so the silicon could be a lot faster, and some could be slower too. It's on the bell curve distribution. Yeah.
Okay, Nguyễn Nam Hải asked a question. I think it's a very good question. You can explain it to him.
I don't see the question. You see it?
Okay, so the question is from Nguyễn Nam Hải. I see in the example images of the conventional, the single source on the left, and the H3, the schematic looks the same, but can you tell the differences between them? So if you look at the schematic, you look at all these gates, right? The buffers, they look the same, but explain the differences between that H3 and the conventional on the left. Yeah, you understand the question?
No.
Okay,
I'm
let
trying
me
to
try.
digest. No, I don't see the question. That's why I'm
Yes,
trying
you
to
see
figure out.
this? This is the gate, right? Inverter, buffer, split in two, right? So from the schematic point of view, it looks the same. Oh, I'm sorry. I'm looking at, but it's similar thing. Everything. So as you have in schematic, you have a buffer here, two buffers, right? They look identical, right? Right, and then 4 buffers right here, and then 4 buffers. So from the schematic point of view, these two look identical. Actually, all of them look identical to each other. Can you tell the difference between these and this, right? So
so this is just example of what the tree look like, but when you actually build them, the routing structure are different, right? This is X, and this is just conventional from A point to point B. There's no structures per se here. When you build this, the tool doesn't know. You have to tell. Believe in. I build this once in Innovus. You have to. There's a H3 spec that you tell it. You crafted. You guided how to build the clock tree in an H formation. So this is just a schematic look. So ignore from the schematic, okay? It may have the same number of structure level at the beginning, but when you come down to the routing different distribution, it's gonna look different.
Yeah. So let me try. So in this case, right? So if you have a clock definition at the output of a buffer, and then you have flops everywhere, right? Flops. Say sorry, I don't have. So I have to draw with the cursor. So you have flop everywhere. So the tree will build and will wire to these guys, and go zigzag, and wire to these guys zigzag. And this is the real routing, right? It can do any of these routing with this approach. As long as it matches the delays and the RC and everything, as long as all these pins will have the same arrival time. So that's this conventional. But the H3, no, maybe I should. The H3 will do something differently. So H3 will say it will build. Okay, it will build somehow of it would say these two flop, and it will have between these two flop it will have these two flop will have wire, and then each of these two wires will be connected through some kind of physical things like that. So you actually physical. This the only difference is that this physical, right? These wiring are wired in such a way is very, very standard. So when you wire here, so it will wire to the midpoint of this H3, and this H3 will split out very evenly like that.
Right,
So
that's the key point you just touched. These tree has to be balanced. These wire has to be equal. Okay, these have to be balanced. All those.
Right. So instead of relying on the tool to do RC matching, you actually build the RC matching wires to guarantee it. And then location of these buffers are important, right? So that's the difference. But in terms of schematic, you look at it, you won't tell, right?
Yeah, this is just a concept from what it looked like conceptually. From the schematic, you can't really tell the difference. The physical structure are different. Okay.
So Nguyễn Nam Hải, we hope that we answer that question.
Okay, so Nguyễn Vũ Thịnh, and why did X3 need a super perfect driver? So for that reason here, because it has to drive these loads here. Okay, because this load may be this load can be depend on the distance, right? The distance depend on where the locations are. So usually it will need a buffer that large enough to drive all the loading, the wire loading and also the sync loading. Yeah, so you put a normal buffer, a regular buffer in here may not be able to drive at all. So usually it depends on the distance. So it can be a big super driver or a medium super driver. So it depends on your design location of the H3 and the distance that you need to drive.
Yeah, but for the basic fundamental class, please do not pay attention to any of these, because otherwise you just think of this one, because otherwise you'll run out of time, doing the labs and all.
So yeah, so the reason I share, so you know what these are in term, okay, you've heard of it. So yeah, I've heard of H3, and at least you can go look up Fishbone, exactly what it's doing. So okay, yeah, we have exactly 17 minutes. Let me go to the labs real quick. Okay. Okay, so in the lab, this is lab 7 CTS. There isn't really much in this lab, so I took the opportunity to show you different things. So here, hopefully, so you need the place up that I did copy it over. So you shouldn't have any problem. I did as a self-contained DB, so you should be able to just source this. So here it says to go ahead and source. So this is run stuff ticker 1. This is just a ticker script here I show. Okay, and go ahead and source this lab. So I'm gonna go ahead and source. Run CTS 1. It should load the DB. All I do is load the DB and it stop right here. The return meaning stop. So it's gonna load the DB. Place op DB. Okay. So here, because of this lab, not much happening here. We haven't talked about the timing debug. So I show you how to do a timing debug, right? So let's go ahead and do timing debug. So you go to timing, and there's a timing debug. So bring up this GUI. Okay. So when I bring up this GUI, just say okay. Default we do setup. So place op only has setup. There's no whole time fix there yet. So this is a way, if you have time violations, this is the GUI way of doing it. But most of the time, I actually don't use this tool because I just take a look at the detailing report and see what it is. But this is just a graphical way of doing it. Okay.
I think Tien went through this already, so you don't need to spend time on this.
Okay, so Tien went through this. Okay, let me just yeah, because there's really not much CTS here on this particular one. We haven't run CTS yet. So let me show you. I think Tien showed this, but I don't think he showed the couple things here. So you click on this, double click on this, it'll bring up the timing path, the path analyzer, and actually you can you can cross probe this thing and it will show you, see the route. So you double click it and actually show you where the path is in particular, in the cross probing in the physical view, right? So it shows exactly where the path is, right? Okay. So you can follow this. This is just the slew rate and the delay bar. You know, this has got the most delay. You can double click on it and it'll bring you to the cells. What cells it is has the delta delay. Same thing with the slew bar, the slew rate here. Which one has the most? Because it has this here. So you can probe and see where it is physical design on your path. Usually it lists the worst path on top. Okay, and you click on the cell, it show you the cell. So cross probing meaning that from here it'll bring you physical to show you exactly where the location of the cell that's talking about. So okay, and then yes, so in this particular, because most of the time the CTS here we talk about concept, so there's really not much in the lab other than a few things that I talking. So we never show you about go back to our blockage. Remember this blockage? This was a partial blockage. Let me turn this off. Can anyone tell me now that we have cells here? What is partial blockage? Why there's only a few cells in this area? Remember, in placement, we didn't have any, an initial version, we didn't have any cells in here. Why do we want to have a few cells in here? What kind of cells is in here now?
Thing is for an inverter that used to optimize the design.
That's right. So this is a soft blockage area only used for optimize. So these guys right here should be either buffer inverter only. Right? You select this, you hit a Q. It should be either buffer inverter only. Can't have any flip flops. So you can see this is a buffer. So we ran place op, right? So this area is reserved for the IPO engine to add buffers or inverters for us too. So all of these in here should be just buffer inverters, nothing else. Okay. So I show you in there all this. There's okay, so did we talk about okay, let me close this. There's a portion of we creating the clock spec. Let me go ahead and close all this. Let's get through this. Okay, creating non-default rules. Okay, so there's a couple ways of doing it. You can do it. Did I show the GUI way of doing it? So you go into edit, create non-default rule. Okay, I normally don't do this way. I just do the I use it the tickle to do it. But this is a thing you can see it come up. It's just a single width. This is we have 9 metal layers. This is the width of metal 1. This is a single width throughout. So in this technology, it's 7 micron, 0.07 micron for metal 27, and spacing is the same. Okay, and then if we create a double width, double spacing, we can go change this to double width spacing and name it 2WS. This is what I had you guys do. Okay. But in the GUI, much easier to do it in the tickle script. See, you can just do create rules and specify metal 1 double spacing, double width would be 0.12, and metal 2, and the rest of them is 0.14. Right? So you can just do this, the tickle script. It'll be the same thing instead of doing GUI. Okay, so I'm just going to simply cut and paste this. And so we name it double width and 2 space. Okay, so it created it. And now we want to create a route type. Okay, with the NDR layers using this particular one. So so the rule which is created here is 2WF. We want to create a route type. We call it clock route. So this is, we name it clock route. And then we specify the layers. We want it to be bottom matter 5, top 6. Okay. So now we create the route type called clock. Okay, which has the NDR rules, the width, and this routing layer, and we want to apply it to the clock nets. Okay, so we want to apply both the trunk and the leaves. So we didn't talk about the trunk and the leaves. So in the clock, the trunk and the main trunk, like the H tree, those are the trunk, and then the leaves is right before it hit the it goes to the lowest. We call the leaves. Okay, so we can. So this is actually applying to the clocks. So this keyword CTS route type. Okay, so we apply the same rule to both the trunk and the leaves, basically all the clock trees. Okay, and then here, this is the tickle. So let's look at get all the clock buffers in the libraries available, right? You can see. Let me move this over. So get live cell clock buffs, because I know it usually clock buffer will be clock buff something like that. So you can just grab the wildcard start, it'll come up. So here clock 12, clock 16, X2, 20. So basically the highest is above 20, and the lower is 3, 2. So is there 1? Okay, so normally we've done is we normally don't use the highest one or the lowest one. Okay, these tend to become the crosstalk victim, and the big ones become aggressor. So in a lab, I had you guys use them just 3, and you can use a little bit more, expand it if you want. So I just use 8, 12, and 16. You can put in like 6 if you like. Okay, so I just had you guys use this set. You can expand and try different things you like. Okay, so one of the way to make sure that it's actually set, just to get DB and this particular variable CTS buffer, and it should come back with the one you just set, right? So you can find out what buffer is set, just to get DB in that particular one. You set DB and then get DB. These are the command from AWS. Okay, we verify that it's actually set. Same thing with inverters. You can do the same thing. Okay, so you go through the motion and set it. Okay. Okay, so here's a keynote in the one important key in the seed engine buffer inverter. By default, the default set is auto. Okay, so it will actually use it will only use by default auto is preferred buffer. Okay, so I notice in Innovus, this variable is a default auto. Most of the time, it's going to use buffers only. Okay, and so if you want to use inverter, we need to set this variable to true. Then it will use inverters. Okay, so I did notice that, so I'll put a note in here. So you can play with this particular setting. Okay, even though we tell it both, but in Innovus it's going to use mostly buffers. So a buffers basically 2 inverters back to back, right? I think we talk about that in the next lecture. Okay, and then we also need to specify, because this library has ICG, so we want to do clock gating. We need to do to tell it what clock gating to use. So I know this is a clock gating cell, so I'm gonna go ahead and the attribute to set gating cell is set DB CTS on score clock gating cell. So one of the way you find out what you can do help, and then you do CTS clock star, and it should come back with all of the attribute that you can set on, clock grouping that relate to clock tree, right? Clock gating cell, clock tree ports, and all different attribute that you can set. So it's quite a few things that we haven't talked about. Okay, so I'll go ahead and set this. Okay, so in terms of the some of the clock trees we just constrained, right? We tell the buffer inverters the layer, the NDR, we applied it. So so that's really the part of the clock tree that I stop here because we create this, we set some of the NDR rules and then we haven't got to the so this is Richard in the lab. I think in the next lab we start with the clock tree spec and we actually start to build a clock tree in the next lesson and the next lab. So this lab kind of short, so go ahead and try this out. Okay, notice I put a .lib. I think before the lab we didn't have a dash live in here. So if you don't have a dash live, it's actually right the db as a link. So to create self-contained, you just do a dash lib, and it will actually follow the link and create a hard copy of all the libraries in here, self-contained DB. So avoid issue that we had before.
So that's the question.
So the question is, in the lab, I've created the wrong rule 2W2S for the wrong metal layer. How do I undo that step?
One way, just create a new rule, the new name, and then apply that rule. So, I mean, you can do the name and then change this, right? Or you create it again, I see, no, actually, the name is wrong. It already exists. So you just create another name and give another the layers, right? Yeah. So the name doesn't really matter as long as whatever you call it, as long as these are correct that you want, and these the rules, the name, as long as it match, it doesn't really matter. Okay. So you create wrong, just ignore that rule. Create another one. Create another name rule that has the same correct spacing and apply to this. Right. There is I think there's command to actually delete route type or something like that. You can delete it if you want, but easiest way is to just do a different name. But I think there is let me see. You can find out. I think is there a remove or delete?
No, I don't think you need to do this. There's another question.
Yeah, so you can do a help. You can figure out on how to do that, but just do a different one. Just create another one.
Yeah, for time's sake, I think there's another question.
Yes, so the leaves. Let me bring back the slide up to talk about the route type. So here, usually we refer the leaves. The leaves are these nets right here that actually drive directly to the leaves, which is these sometimes the loads are called the leaves. So think of a tree, the leaves at the very end, which is the flip-flop, right, to the cell. So these are the leaves. Okay, the trunk are these guys. We call trunk. Okay, and there's another term called top. If you have in a spinal thing, you have a big long one. The top is basically these guys from the source to the buffer is called the top. Okay, so the rest of these are trunk and these are leaves. That's what it meant. Okay. So when you say connect the leaves pin using this rule, this is what it's talking about, this level in the trunk of the rest of these guys. And then there's another terminal called top. If you don't search the top, it's going to use the same as the trunk. Okay, so hopefully that answers your question, man. Okay. Any other questions? So yeah, so play with this in this lab, experience with it. In the next lab, you actually get to build the trees and see what's happening during CTS. Okay. So
the the integrated clock gating cells, typically you don't need to specify because they're attributes in the library that really have them defined, so the tool will look for them. So in the lab, this is just showing you if you don't have that attributes in the library, you can set them on the command line, but in practice, you don't need to do this. I just want to make sure people understand.
Yeah. Thank you, Phil. Yeah, that's true. So the CG cell will have an attribute is ICG. So you look a little bit file, you see that cells. Some of the special shell will have the special attribute. The tool automatically recognize it. Okay, we'll have fun with the labs. This is short labs. Play with the timing debugs if you haven't had a chance to do it. And then in the next lab, we'll finish up with CTS, and you'll see your clock trees and the results of it.
Yeah, I won't be surprised if some of you already got lost. So please take a look, read the manuals, read the watch the videos, and read the slides. And next week, when you come back, if you still need to have something explained, feel free to ask questions.
Yeah,
And so
so
we can also have the students asking questions in the classroom through the stream. So if you've got a question
yes,
related to this.
yeah, and then we'll try to go answer. Yeah, so the clock's TTS is a very important step, okay? Because if you have a bad, you're going to have a project at the end coming up at the end, right? You're going to have your own project. Each student will do your project, and we have constraint targets, for your design performance. And if you don't meet one criteria, is that you have to, if you build a bad clock tree, you're going to have a hard time closing your hold times. I'll meet your performance, the target performance. Okay, so it's very important you understand, because you have a lab that you and another project that you need to do at the end to complete as part of your course certification. So it's important that you understand how to control the clock tree. If something went wrong, where do you go about fixing it, and how you set constraint? How you figure all this out? Okay, all right. So we 2 minutes over. Thank you for your time, and we will talk to you guys again on next Tuesday.
Now you can go drink and celebrate your birthday.
Recording
Bye.
stopped.
Maybe tomorrow. It's late now until it's 11, but we'll do tomorrow.
Happy birthday.
All right, thanks all. Bye now.
Bye.